I told you yesterday that you have to know the names of this chemical formula. This is CH4. This is methane. You have to know this one, that ammonia. Of course, you already know this one, I hope. Right? Water. Okay. I'm going to tell you the name of this one, but you don't have to know the name of this one, okay? These are names you have to know. This is not one you have to know, but this is formaldehyde. No, you don't. Well, I mean, it would poison you, yes, but formaldehyde is used for preserving, like animal samples. Like parts. Like if you were to put a brain in a bottle, you put it in formaldehyde. Okay, for example. Okay, animal parts are stored in formaldehyde most of the time. Yes.
What did you say CH4 is?
That's methane. Okay, and this is ammonia, and that's water. Okay. All right. So with this formula here, I can't. It's the kind of thing where I can't just give you hydrogen, carbon, and oxygen and ask you to find a molecular shape. It's not quite that simple. You kind of got to know how many of each element or each atom go into that formula, and then you can figure out the shape. Okay, so let's write out all these symbols and their electron dot formulas. Okay, as separate things. So write the electron dot formulas for 2 separate hydrogens, for 1 carbon, and 1 oxygen. Okay, do that now on your paper. The electron dot formula for 2 separate hydrogens, 1 carbon, and 1 oxygen. And you need your periodic table for this stuff, always. Okay? You can't figure out, well, I don't know, maybe you've got to memorize, but I've got to memorize, but I've been using this for years and years and years, right? But you would have to look on your periodic table to figure it out. So hydrogen is right here in position number 1. It can only have 1 electron. The first sublevel you come to is S. And there's only 1 electron there you can put on hydrogen. So the hydrogens are going to have 1 dot. All right, its valence level is going to have 1 electron in it. Carbon's here, and so in this second primary level, that's carbon's valence level, the second primary energy level, carbon has 2 electrons in the p sublevel region, which we can represent as being boron and carbon. It's not actual boron and carbon, but it's 2 electrons that are represented by those 2 elements there, and then 2 over here in the S sublevel region, represented by lithium and beryllium. So that's a total of 4 electron dots for the valence level electrons in carbon. So carbon has 4 dots. And oxygen then has 4 electrons in the p sublevel, represented by these elements, plus the 2 over here. So everything in this row up to that element tells us how many electrons there are in the valence level. Okay, we spent a lot of time in the last unit writing orbital notation to understand how that works. But then oxygen then has 6 electrons, 1, 2, 3, 4, 5, 6 in the valence level. So we'll put 6 electrons around oxygen. All right, just a reminder from the past couple of days, of class days anyway, that elements like oxygen and carbon want to have 8 electrons around that valence level. So it wants 8 dots. Okay? Hydrogen only wants 2. So what we're going to do is try to figure out how to share electrons in a way that gives all of these atoms the electrons they need to be as stable as they can be. Okay? So I can tie, say, 1 hydrogen here and another hydrogen, share it here. And I need to come up with a way to give carbon 1 more electron. Right now this carbon has 7. 1, 2, 3, 4, 5, 6, 7. This oxygen has 7. 1, 2, 3, 4, 5, 6, 7. What? Yeah, the bottom ones can share. So that will be a double bond then, okay? So this would be a reasonable sharing arrangement for these elements, okay? Then to get a Lewis dot formula, we're going to squeeze the electrons between the element symbols. So I'm going to put the carbon here, and I'm going to squeeze these two electrons together between this hydrogen and this carbon up here on top. I'm going to squeeze these two electrons between this hydrogen and that carbon. So these two get squeezed over on this side. Okay? Between the carbon and the oxygen, there are 4 electrons. And what I showed you previously was when that happens, you squeeze them together in that sort of form. Okay? And that's going to give us then a Lewis dot formula. All right, from the Lewis dot formula, then we can do a Lewis formula where we replace shared pairs of electrons and only the shared pairs with lines. I'll just replace shared pairs with lines. So here's our carbon. Between the carbon and the hydrogen here, there's one shared pair of electrons. That's a single line. Between this carbon and hydrogen, there's a single line for that shared pair. But between the carbon and the oxygen, there are 2 shared pairs. Okay? So we need 2 lines between the carbon and the oxygen. And then we can put the remaining electron dots. Okay? So then this is the Lewis formula. Okay? Now then, going back here to the Lewis dot formula, this is where we go back and count the sets of electrons around the central atom. Okay, now you don't have to circle these. I'm going to circle them for your benefit to show you where the sets are. There's one set here, there's another set here, and these 4 electrons make up a set. All the electrons shared between 2 atoms make up a set. Lone pairs, if there were any, would be a set. Okay? So, sets are, and I told you that we're going to count the sets, but I didn't define sets yesterday except to say sets could be 2, 4, or 6 electrons. Sets are, a set would be all the electrons shared between 2 atoms, and also lone pairs make up a set. Okay? Okay? So by that definition, we have 3 sets of electrons around a central atom. Does that make sense to everybody? All right. The central atom in this case would be carbon. Yeah. The central atom in this structure would be carbon. So when we start doing the 3-dimensional arrangements, then we're going to put carbon right here in the middle. And our goal in this electron dot shape, this 3-dimensional shape for our electron pair shape, I said electron dot shape, but the electron pair shape, is to get these sets as far apart as possible. So we're trying to arrange them in space so they're as far apart as they can get. And to do that, we're going to put them at 120 degrees. Okay, that's as far apart as you can get those sets. Okay? Two of the sets have 2 electrons, or a pair, and one set has 4 electrons. Okay? So we spent all of yesterday in class figuring out the different kind of molecular shapes you can get from a tetrahedral electron pair shape. But this is not a tetrahedral. A tetrahedral has 4 arms equally spaced around that central atom. This only has 3. Okay? This one is trigonal for 3, trigonal planar, because it's pretty much flat. Okay? I mean, its three-dimensional shape still is kind of a flat shape. Okay? It's called trigonal planar. And this is the electron pair shape. All right? All right, from that trigonal planar electron pair shape, we're going to follow the same steps we did yesterday, where we're going to redraw the same drawing, every detail of that same drawing down here. And then we're going to go to the Lewis dot formula and find where those electrons are shared, and replace only the shared pairs of electrons with the atomic symbols. Only the shared pairs of electrons get replaced with the atomic symbols. In this case, all these sets of electrons are replaced. The 2 single pairs here get replaced with hydrogens. The double pair gets replaced with an oxygen. Okay? No, we don't worry about that, because what we're interested in is the molecular shape here when we're done. Okay? So these 2 right here, these 2 single pairs, get replaced with the atomic symbol for hydrogen. And the double pair, the double bond, gets replaced with a symbol for oxygen. Okay? And when we're done with all that, we have a molecular shape, because there are no more lone pairs. If there were lone pairs left on these arms out here, we'd have not a molecular shape, but a modified electron pair shape. But since we replaced all the electron pairs around it, then we're at the molecular shape. We have arrived at the molecular shape. So this is still the same geometric shape. It's still 3 arms, flat. It's a trigonal planar shape. But now it's not the electron pair shape, because we have atomic symbols around it. It's not the modified electron pair shape, because there are no electrons along with atoms on the arms. This is the molecular shape. Does that make sense? Modified electron pair shape. If there were both element symbols and electron pairs still around this thing, that'd be a modified electron pair shape. Right? We don't get to the molecular shape until all the electron pairs are eliminated. Okay?